White in the College of Science. Welcome. This is the sixth seminar this year. How many went to all six? Anybody? A few of you? I know Chris went to all six. Thank you for doing that. We're going to have six more next year. If you have any ideas for speakers, feel free to share those ideas with me or whoever the new dean is for the College of Science. You may know Henry White, the dean of the College of Science, is stepping down, and I believe pretty soon there'll be an announcement of who the new dean is. And I was planning to embarrass Henry tonight, but he's not here. He's on travel. But I have a feeling he'll watch this event. I know he usually watches these if he can't be here. So if you would, join me in a big, loud round of applause for Henry for everything he's done. So I have to say I've only been here a little over 2 years, and Henry has been an incredible person to work with. And the College of Science is this incredibly collaborative college, and so I really appreciate everything Henry's done for me in my college, but also I really appreciate the College of Science. So I'm going to turn the microphone over to one of our faculty to make an introduction tonight of our speaker. I think you're going to enjoy the talk tonight. And by the way, thanks for coming on this beautiful evening and on a Tuesday. We threw everybody off. I think it's harder to get people here on a beautiful evening than it is when it's snowing and hailing outside. So thank you for being here. And I'm going to let Dr. Pete Lippert, who's an assistant professor of geology and geophysics, introduce our speaker. So Pete.
Thank you all for coming tonight and participating in our final Frontiers of Science this evening. It's my distinct pleasure to introduce our final speaker, Dr. Lindy Elkins Tanton, who is visiting us from Arizona State University, where she is the director of the School of Earth and Space Exploration there. Dr. Elkins Tanton is a planetary scientist, an educator, and a thought leader who focuses on the evolution of terrestrial planets and the relationship between Earth and life on Earth. So there's a lot of really cool things that we're probably going to learn about in this lecture today. Dr. Elkins Tanton, as I mentioned, is the director of the School of Earth and Space Exploration, which is a really interesting school, an innovative school combining engineers, scientists, planetary scientists, and a variety of different academic units under a single umbrella. She's the co-chair of the Interplanetary Initiative, which is a really neat education and science initiative. She's co-founder of Beagle Learning, which provides strategies for active, engaging learning for all. And what she's here to tell us about today, she's the principal investigator of the Psyche mission, which was selected in 2017 as NASA's 14th mission in their Discovery program. She received and earned her full collegiate education at MIT. And prior to earning her PhD at MIT, she was a lecturer in mathematics at St. Mary's College in Maryland, and she was also an analyst and a writer for a variety of different publishing units throughout the Northeast of the US. Following her PhD, she immediately joined the faculty in that department, and then a few years later moved to become the director of the Department of Terrestrial Magnetism at the Carnegie Institutes. So those of you who are into science and planetary science may be familiar with a lot of Carnegie's work. And then from Carnegie, she went to ASU. Dr. Elkins Tanton is well known and published for her science on drip magnetism, flood basalt magmatism, magma oceans, and the structure, composition, and evolution of planetesimals, or the building blocks of planets, so something we're going to learn more about tonight. She's also well known for her team building and her leadership in education and science administration, and her innovative and, at sometimes, some people would call radical classroom learning environments, which are actually super cool and engaging. And those of you interested in science education, I encourage you to explore Dr. Elkins Tanton's contributions in this field. Her accomplishments have earned her many awards and distinctions. I'm not going to keep you here all night telling all of them, but there are a few that I do want to highlight, one being an NSF Career Award early on in her academic career, something all of us young faculty aspire for and hope we get because it makes our career in many ways. She's a fellow of the American Geophysical Union, and in 2018, she was elected to the American Academy of Arts and Sciences. On top of all that, because that's not enough, She also has an asteroid named after her. So that's a pretty cool thing to have in your life as an asteroid. So check out asteroid 8252 Elkins Tanton. That's named after our speaker tonight. So if you can't tell already, I'm really excited that we have Dr. Lindy Elkins Tanton visiting and sharing her work and time with us tonight. And I'm going to turn it over to her, and we're going to learn about the Psyche mission. Thank you.
Thank you so much. That was a really lovely introduction. I'm really touched to be here and excited to share with you all the Psyche mission. This is a big NASA mission. We have not launched yet. We're in the formulation and about to begin the really official build stage. And so what we've done is we've made what we call a mission trailer. Like you have a trailer for a movie, we have a trailer for our mission. And so I'm going to start by showing you that mission trailer. And it's 5 minutes long, and then you'll have all the structure to follow what I'll be talking about next. Let's see if I can do this in some nice way. Here we go.
It's a shame, but living in the city, very rarely do you get to see stars.
I feel like I have a new connection to them in a way that I haven't before.
From out in the desert and I look up at the sky, you just see millions and millions of places that we should be going.
It's almost baked into our DNA, the desire to go and explore, right? That's the whole reason why we left the forest and then traveled across oceans just to see what's out there.
I was born in 1969, which is the year we landed on the moon. So I am a space baby.
When I was a kid, the guys driving cars on the moon. They're driving cars on the moon. That's so cool. I want to do that.
All the rocky planets that we know of all have got a metal core in their center. And especially for the Earth, it's the source of our magnetic.
Our magnetic what? We're never going to know the answer. What is this? Oh, it's just, wait a minute. Okay. Hold on to that thought. Don't forget how enthusiastic you're feeling while I remember to turn back on the Wi-Fi. Forgive me for that. I know I should have it embedded in my PowerPoint, and in recent times I have not been able to succeed at doing that. I suppose I should have absolutely gotten some brilliant person to make that happen for me before coming up here. But instead you can just be amused that we can
We don't know
do
a lot
this.
about our core. What we learn about it, we learn indirectly. Can't go there.
It's too hot. Pressure's too high. Instruments would melt. Can't drill a hole that deep into the Earth or other planets. But turns out we can study the planetary core out in space because there's this one object called Psyche.
16 Psyche is an asteroid that orbits the sun out between Mars and Jupiter.
It is the only asteroid that we're aware of that is 95% metal or more and is really huge. It's about 200 kilometers across in one axis.
So it's about the size of Massachusetts.
It's believed that it may be a remnant core of an early planetesimal that was formed in the very, very earliest parts of the formation of the solar system.
And after this planet started forming and this metal core formed inside of that, it collided with other bodies that then stripped off the rocky metal, leaving this core in place.
The first thing that came actually was the theory. Some people from Jet Propulsion Laboratory contacted me and said, we would like to plan a mission that would test your hypotheses.
And that starts you down a road that takes years. So we wrote a proposal to send a NASA spacecraft to visit this big ball of metal. And then about a year ago, Lindy gets a phone call. You win. And then we're all like, oh my God, now we have to do it.
Psyche gives us the opportunity to visit a core, the only way that humankind can ever do. And it would be the first metal object that humankind has ever visited.
We've been approved to go in August of 2022. So we talked with our mission design and navigation team, and in fact they were able to come up with what's probably the most optimal trajectory, doing a Mars flyby.
Flies past Mars, gives us a gravity assist, uses that propulsion system to then slowly creep up. So at the end of 2025, getting there in early 2026.
SSL is building the solar electric propulsion chassis. When we do the mechanical, physical integration of each instrument on the spacecraft, We'll work hand in hand with each of the providers to get out to Psyche and do a full discovery mission.
We figured out a way for many, many people to build something together so complicated no one person can understand it, but it all has to work together perfectly for decades without fail.
Just the fact that these things work at all is a thrill. It's just a testament to the engineers at JPL, the companies that we collaborate with, that they can build these things.
It's exciting for me to be able to be a woman winning and leading a deep space mission. The only previous woman who competed, won, and led a deep space mission was Zuber, who was my friend and mentor at MIT. And so my drive is to make everyone feel welcome and to have every voice heard. We want as many undergraduates as we can. We want to involve as much of the public as we can. We want people to feel like this is their mission.
You get that first picture back, and one of the first things goes through your mind is, oh, thank God I didn't leave the lens cap on. We'll put our pictures out there as soon as they come down. So we'll discover at the same time that the public discovers. We'll be scratching our heads and say, I don't know what's going on. At the same time everybody else is like, wow, what is that? I don't know, let's figure it out.
I did get to look at Psyche through an optical telescope in my backyard. Some wonderful colleagues brought over their telescope on a fortuitous night. It's a very, very tiny, faint dot. And that made a bunch of us cry to think that we could send something to investigate that speck of light.
We can understand this universe that we live in. We can explore it, we can learn about it, and we can be a part of something which is much bigger than just us or just this planet. We will see new things when we visit a world made of metal.
Yay, Psyche. All right. So that's what we call our mission trailer. Trying to explain what the thrill is, explain what we're trying to do. And that film is made by a local company in Phoenix called True Story Films, and they actually won a regional Emmy Award for that, which I thought was kind of cool. So I was just trying to bring more people into the team. So first I want to tell you a little bit about why Psyche and what we think Psyche is, and I'll talk about the science, and then I'll talk a bit about the spacecraft that we're building and the team that we have and the schedule that we're on, and then we'll have a conversation about whatever it is that people are interested in. So this is a timeline, a little schematic timeline of our entire age of our solar system. On the far left is what we call the beginning of the solar system, maybe the first solids that formed out of the gas disk around our growing young star. Those first solids, we can actually date them back to 4.568 billion years ago. And then on the far right is us in the present day and the billions of years in between. The green bars are showing evidence for life, and we have evidence for life very far back. And something that's relatively new in science, maybe in the last 10 or 15 years, is the fidelity with which we can now date the happenings of the very earliest part of the solar system. We now know with really quite amazing exactitude when certain things were happening in the very beginning of the solar system. So that's where we're going to go with the Psyche mission. Notice that there's this blue bar, first evidence for water oceans. It should really say first evidence for liquid water on the surface of the Earth. But many of us were taught, including myself and probably many of you in school, that the beginning of Earth was called the Hadean because it was supposed to be like hell. It was supposed to be all volcanic and all incredibly hot, all the leftover heat from accreting the planet. But it turns out the planets cool off and become clement and habitable incredibly fast. And so we've really just got 270 million years between the very first little sand grain solids that formed in our disk spinning around our sun to the time that they had built up to make something which is the size of the current Earth and had cooled off so that there was liquid water on the surface. So just 270 million years to do all of that. It's like a snap of a finger. So I used to tell my students, I haven't been doing this recently, but I used to tell my students, but the only thing I absolutely required them to memorize was the number 4.568 billion years ago, the age of the first solids in the solar system. I used to tell them that they would fail the course if they couldn't recite that to me. So sometimes when I'm feeling really uppity, I make audiences say it out loud, so I might make you practice later, so just remember 4. We are at a university after all, right? Okay. So here we are in the 270 million years. We're very interested in these things that we call planetesimals, which Pete very nicely mentioned for me. So if you imagine that this guy on the upper right is the Earth and in the very, very hot stages of accretion, and then imagine at the far left these little gray dots and then the gray and red dots, these are planetesimals. So this is what these sand grains very rapidly formed up into, bodies tens to hundreds of kilometers in radius. You know, smaller, maybe up to the size of the moon, so pretty big, maybe not as big as Mars. And we know from the meteorite collection that some of these formed as quickly as 500,000 years. 500,000 years, not even 1 million years, not even 10 million years, like an eye blink. They formed, if this was a 24-hour day, our solar system, they formed in the first 3 to 5 seconds of the day they formed up. And they had inside them this radiogenic element, aluminum-26. We've all got plenty of aluminum in our lives now, but there's no more aluminum-26. This is a short-lived radioisotope that just existed in the very beginning of the solar system, and it was enough to heat up these planetesimals to the point that they melted and did what we call differentiation. The metal sank to the middle and made a metal core, and it left a rocky outside. So the same structure that the Earth has today, that Mars has, and Mercury, and the Moon also has a little tiny metal core, and Venus, these guys formed them way back in the first, virtually 10 seconds of our 24-hour solar system, if you imagine it that way. And we know this from the meteorite record. So some of them melted and formed cores, which are shown there with red. Other ones just warmed up. They didn't melt all the way. And so most of them circulating around our sun in this wild, high-energy early solar system crashed into each other and accreted together to make bigger and bigger bodies till they made things the size of Mars that we call planetary embryos, and then finally some of them came together and made the Earth. And so an interesting piece of new science in just the last few years is we now know that Mars formed within 3 to 5 million years after the first little grains of sand. So fast, so fast. But some of these poor planetesimals did not go through accretionary impacts. Some of them went through what we call hit-and-run impacts, which you saw on the cartoon. We realized as we were writing this proposal to these NASA review committees, most of whom had never heard of the asteroid Psyche. And you have to be quite the asteroid aficionado to know all the named asteroids, even the ones that were named in the mid-19th century, to explain to them why this was so exciting. And we realized partway through that we had in our minds a kind of a videotape of the process that we think created Psyche, and we were designing a space mission for that, but nobody else had that videotape in their head. And so that's why we hired that artist to make that videotape that you saw a bit of, that animation of a hit-and-run collision knocking the rock off the outside of the planetesimal and leaving its naked metal core out there in space. And so some people who study these dynamics say that about half of the collisions between bodies were accretionary and built up the upper path, and about half of them were destructive and what we call hit-and-run collisions and went down the lower path. So that's our best guess for what Psyche is. There are only, that we know of, 9 asteroids out of our literally millions of asteroids that are made of metal. And there's only one that's large, and that's Psyche. So there's only one object like this in our whole solar system. We think it's the only core, if it isn't a core, that humans will ever see for the whole length of our species. So now that's that image of a hit-and-run collision hitting the rock off the outside. Now here's an interesting thing about a hit-and-run collision. Our models say that it would take 4 to 8 of those to knock all the rock off the outside of a planetesimal, and you had to have no accretionary collisions in between. So does that seem really likely? No, it's not so likely. It's not so likely, actually. But still, it's our top hypothesis. So I'll return to this through my talk, what we actually think Psyche is. And all of the ideas we have range from the improbable to the really improbable. Like, we don't really have any really great, that's definitely, and by the way, I do always ask people if they have other ideas about what Psyche could be, and just in case you had it in mind, it is not the Death Star, because I've brought this up in talks before, and people who are truly experts in Star Wars explain to me immediately that the Death Star is much larger than Psyche, because they know the dimensions, and not even the model of the Death Star is not even the right size. So it's not the Death Star. That's the only thing I know for sure. All right, so we think that it then cooled, and you can see here what I'm showing. Let's see. I'm doing the wrong thing. There we go. Oh, okay, I really did the wrong thing, sorry. Doop, 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 doop. This is Pete's thing, and I didn't practice with it first, a very bad habit. Okay, so what you're seeing here is I'm imagining that this molten metal core froze starting on the outside. So that's now solid iron nickel metal. And you can see some brown flaps, that's some of the rock of the original exterior of the planetesimal falling back onto it. And then what are the purple things there? That's the magnetic field. And so if it's a liquid iron nickel metal and it's rotating fast enough, it would make a dynamo, make a magnetic field, the same as our Earth has. And it turns out, and maybe you don't know this because I didn't know it either, almost all the iron nickel meteorites that fall to Earth record a magnetic field from their parent bodies. So we think it was common for planetesimals to have magnetic fields. And we really hope that Psyche has a magnetic field, because that would be a slam dunk, 100%, this was a core. We have answered our top question, what is Psyche? So that's what we hope. And I also would like to encourage all of you to draw magnetic fields in purple forever, because I think that they're purple. So it's kind of, it's a good color for a magnetic field. And so we think that it continued to freeze, and then here's a really cool idea. It turns out that as you freeze gradually iron nickel metal, if there was some sulfur in it, the sulfur comes out and it makes an immiscible second liquid like oil and water. And it turns out that sulfur-rich liquid is also low density, and we think that it would erupt onto the surface of Psyche in sulfur volcanoes. And you'll also notice, and this is for people who love, are there some people from metallurgy here, by the way? Yeah, okay, because I have a few metallurgical things for you guys. This is one, and then there's one at the end. So iron nickel metal, it turns out as it freezes, it loses 7 volume%. So if it's freezing from the outside inward, it'll form a hard shell, and then as the interior continues to freeze, that shell will have to contract to make up for the contraction of the freezing. And so we think that it would form contraction scarps on the surface, breaks through the crust as it contracts, and that the sulfur volcanoes could erupt through that. And so they will not be erupting now, even if this is true. This would have happened, 4.560 billion years ago, something like that. But we hope to see the remnants of it. So that's what we're going to be looking for. So that's our hypothesis, and that's what we're hoping it'll be. And so now this image right here, this is by the same artist who did those hit and run collision. His name is Peter Rubin, and he is actually a Hollywood sci-fi film artist. He made a bunch of the ghosts for Ghostbusters, and for about 2 years while we were going through part of this proposal writing process, which by the way took 6 years from the first idea to getting selected by NASA. It was 6 years of constant work on proposals. And he and I would Skype on Sundays, and I would try to explain to him the science that I'm explaining to you today so that he could draw an image that would transmit that. And so also in the video you saw the animation of the beautiful 5-panel solar array Psyche spacecraft coming up to the big rocky Psyche asteroid, and that is all his work. And and everything you see in there is based on well-posed scientific ideas. But here's a really important thing. If you come away with anything tonight, I'm going to tell you probably everything I tell you tonight is wrong. Because every time we go out into space, we get surprised and we discover things we never imagined. And now we're going to a kind of body that no human has ever visited. And that in fact, despite our wonderful imaginings, we've never seen as more than 2 pixels in Hubble. We do not know what Psyche looks like, and we do not know what it's made of. And so everything I'm telling you today is just the process of the best kinds of scientific guesses we can put together. Probably wrong. Okay. So this is the cover of our step 1 proposal. So first that thing happened, I wrote that paper with Maria and Ben, and then we got an email from JPL and said, let's think of a mission, and then we started thinking of the mission, and then we decided we would work with JPL, and then pretty soon we've got a team of say 20 or 30, and then we're getting ready to write our step 1 proposal, and we've got a team of about 50 or 60, and our step 1 proposal is about 250 pages of everything that has to do with the mission, from the science through the engineering and the schedule and the budget and the team and everything that we need. And we competed with 28 missions in that step 1. And this is the cover of our step 1 proposal. And now you know that this is the moment of a hit and run collision. Now you can see what I'm trying to demonstrate with this picture. And this one that we showed in the beginning, this one, this is about 30 seconds later, right? While that hit and run impactor is screaming off down to the bottom left, and you can see the rock being stripped off of the glowing liquid metal core underneath. And so we're even trying to make an animation with the covers of our proposals. And so with those 28 proposals that went in step one, I'm just here to say that there were many reasons why we were not going to be selected. Normally when someone is trying to win a Discovery class mission or a New Frontiers, which is the other big kind of mission you can propose for, often you have to go through the whole process at least twice. You kind of get the whole thing tuned up every time. I cannot even imagine. I mean, the blood, sweat, and tears is unbelievable. We brought in SSL, which is now known as Maxar, as our industry partner, not Lockheed, not Ball, not Northrop Grumman, but a new company that does telecommunications satellites around Earth, but they'd never done deep space. So we assumed that we would be crossed off the list right away because we have a new partner. Plus, this new partner, one of the reasons we chose them is that they build spacecraft exactly of the kind that we need. And they built them so many times that they could give us a firm fixed price. And that firm fixed price was $100 million less than what it would cost to be built by hand and specially the way it normally is for a NASA mission. And so we broke the NASA cost model because NASA has a very specific cost model where you put in all the things you're doing and then they tell you how much it's supposed to cost. Of course, that actually takes several months and a huge team of people. It's not like just a plug and play Excel spreadsheet. But we broke their cost model and we had to convince them that was right. Plus, I'm the first time through PI. I hadn't done this before. So all these reasons we'd never be selected. But we were selected for step 2. So 5 missions were selected for step 2. And each of us was given $3 million for 1 year to write the concept study report, which is what this is the cover of. And that's an 1,100-page document explaining everything about the mission. And there's also, I actually really love describing the site visit when the NASA reviewers come out and grill us, which I'm not going to do right now because I don't think there's time, but I'm happy to do it later if you're interested in what the ultimate review session of all possible review sessions is like. And it turns out $3 million isn't enough. It turns out it takes $5 million to write a concept study report and do all the things you have to do that year. And so SSL and ASU and JPL all pitched in, and we put it together. And by the end of that year, our team was 140 people, and we still weren't selected. And then on January 4th of 2017, so just over 2 years ago, I got a call from the NASA Associate Administrator saying that we were selected for flight, which was an extremely surreal moment. I'm here to tell you. And it was just what Jim Bell said in that video, like, oh my God, now we have to do it. How did that happen? And so that was very life-changing, and that's the path that has brought me here today. So this is how big Psyche is compared to both Massachusetts and Arizona. It's really quite big. It contains about 1% of the mass of the whole asteroid belt. And this is what it in fact looked like through the telescope, the same picture from the video. Just a spot of light. And like I was saying, through Hubble, it's only 2 pixels. We really don't know what it's going to look like. So I'm giving you all these beautiful images, and they're almost certainly wrong. So I keep trying to remind people that even though we have pretty pictures, we don't know what it looks like. One of the things we're curious about is what will impact craters look like when they go into metal? We know what impact craters look like in rock. You can look at the moon every night and see giant impact craters. You can go to Meteor Crater in Arizona and other craters, and you can see what they look like when they end up in rock. And we know what they look like in ice from icy moons. We've never seen an impact crater in metal. When you do them in the lab, so you see that's not actually the impactor that made that impact, because the impactor that made that impact is now smeared all over the inside of the impact and in a plasma stuck to the sides of the walls of the chamber with the big gun at Ames Research Center where this was done. But it's the size of the impactor. And you see how deep that crater is, so it's a much deeper bowl than what you get with rocks. And also with rocks, those ejecta flaps that are sticking up on the sides, they fall over. But here they froze before they fell over. So we don't think that the ones on Psyche will freeze because the scale is too big. The heat would have to conduct all the way through that flap and freeze before it would fall over. But something might form. And we haven't done all those calculations yet. That would be a pretty fun little thermomechanical set of calculations to do. But we think they're going to look different, so we're really curious to see what they're going to look like. And we've been doing some more experiments of our own. This is an Ames Research Center impact, that's somebody's thumb for scale, into an actual natural iron meteorite. And a couple things to look at are, now I'm afraid to do this because I forgot. Is it the top one, Pete, or the bottom one? The bottom one. The top one. The bottom one. Okay, there we go. Now I'm not afraid anymore. So do you see these crevasses, these cracks that go radially around the crater? We don't see anything like that in rock, and we wonder if we'll see giant annular crevasses in the craters on Psyche. We don't know. And then here are some of these frozen flaps, and then here are some big radial cracks away from the crater, and we don't know if that physics will scale or not. But anyway, there's a lot of interesting things to wonder about what Psyche's surface might look like. And then there's this beautiful kind of meteorite called a Palasite. So how many of you know about Palasites? A few people. Yes, some people know about it twice, which I like. Yes, Palasites. So Palasites are these beautiful meteorites. Very few of them have fallen to Earth, but we have some selection of them. And they are, in fact, iron nickel metal. That's what this gray stuff is. And these green gems are olivine, the same as peridot. And sometimes it's pyroxene instead of olivine, but they're gorgeous, especially when you slice them really thin and polish them and shine light through them, right? Well, not their natural state, but very beautiful. And there's some indication that parts of Psyche's surface might be made of this. And that would be kind of cool. That would be the remnants of the rocky outside of Psyche before it was stripped off. So who knows what it's going to look like. So here's our partnerships, and this is what our model of our Psyche spacecraft looks like. 5-panel solar arrays on both sides. ASU, we're the lead, and then Jet Propulsion Laboratory and SSL are our NASA manager and our commercial chassis builder. And then we have all of these other team members from around the country and around the world picked very carefully for their particular skills that we needed on the mission. So right now, we've been at this since January of 2017. Our team's up to about 550 people. We'll be going to about 650 people spread out around this whole set of organizations. And so it's a really, really interesting process of team building. On the one hand, there is something of a system because NASA's used to doing this. But then there's the freedom to make changes also, which I have tried to do. I've tried to do things like very often when people are beginning to plan a mission, they kind of get their friends, their science friends around them and start planning the mission. And very often those science friends are people who build instruments that fly on spacecraft. So then it gets really, really awkward when it turns out you don't need their instrument on your spacecraft. And then you have to decide, do we torque the mission to include the spacecraft, or do I throw my friend off at the team and ruin my friendship for life? And so we were very, very careful to start with the science, gradually build to what instruments we needed, and then invite the instrument providers to join the team. And we only made one mistake. I only made one mistake by inviting someone too early and then having to throw their instrument off. And ironically, that was Maria Zuber, my friend and mentor from MIT, who ran the only other, that was the Grail mission to the moon. And so I was a little nervous. I sat down with her over breakfast. You know, Maria, I'm sorry, we're not going to be able to fly your laser altimeter. We just don't need that fidelity of altitude. We're going to do it all with radio science. And first she said, well, that's it. I'm done. I'm off the mission. And then she's like, no, it's too cool. I need to stay. And so she stayed on the mission, and so she'll be helping us with the calculations, which is great. So many interesting things about team building and the creation of a good culture. I'm sure you've all heard about the very, very sad Mars lander that flew, you know, and we knew it was just about at Mars, and then it just never talked to us again. And it turned out that it was literally an English metric conversion error. Do you remember that terrible story? That is a true story. And one of the things that we've tried to work on really hard in this team is to make sure that everyone's voice can be heard all the time, and that there's no discrimination between the excellence of a comment from the lead project scientist. By the way, the people you saw in that video are the leadership team for Psyche. They're not actors, and they're not bit parts, and they are our lead systems engineer and our deputy systems engineer and our payload manager and our project manager, and then the imager lead and some other people. And so we want everybody's voice to be heard, because the very best news there is a problem that you hear about early. That's the best news there is. And so making sure that everybody knows they're not going to be yelled at or beat up or have any problems caused for them if they bring trouble forward, because that's the best thing. And so trying to set that culture early has been really important for us. All right, so here's the project timeline from 2017 at selection. over here on the left, up to arrival at Psyche in January of 2026. I wonder how many of you have experience with this engineering timeline of PDR, CDR. Are these acronyms that make sense to like one or two people? So this is a sort of a standard systems engineering approach to large complex problems. And PDR is preliminary design review, and CDR is critical design review. And then these other guys I'm not even going to go into. These are other NASA acronyms. But we've been coming through the formulation phase of phase B right here, and we're getting ready for NASA to give us the final go-ahead to go into phase C and D, which is implementation, or what I call build and launch. And so even though we're technically still in formulation, one group has begun building already because the timeline requires it, and that is SSL. They're actually laying up the composite for the giant cylinder that's the inside of the spacecraft chassis. Now, unlike the standard engineering project, we don't just have one PDR, not just one preliminary design review. We have 18 preliminary design reviews. And so they started last September and they lasted through this March. And I refer to it as festive PDR season. And so if any of you follow me on Twitter, you saw I use that hashtag a lot, festive PDR season. And the season of giving, the season of receiving PowerPoints in your email every day, you know, the season of receiving requests for action. And so every instrument has its own PDR, and every subsystem has its own PDR, and then some subsystems have just tabletop reviews. So we had 10 tabletop reviews and 18 PDRs. And then in March, we had our project PDR, which was a full 5 days with the entire team, probably 250 people out of the team at Jet Propulsion Laboratory, and our NASA governmental appointed review board, standing review board there, checking us on every single thing. So went through PDR extremely well, actually. Really, really made us all extremely happy. And then in the intervening weeks between then and May 23rd, when we go to NASA headquarters and hopefully get the go-ahead, we're cleaning up all those requests for action, you know, brushing through our budget one more time. I was on the phone an hour ago because of a budget problem. And then when we'll go to NASA headquarters and we'll give them a presentation, and then what we hope we go through what's called another 3-letter acronym, which I now call TLAs, 3-letter acronyms. It's KDPC, Key Decision Point C. And so that is right at that vertical line right there when NASA hopefully says, yes, go ahead to build and launch. And so we're at this kind of key moment. But guess what? There's also festive CDR season, Critical Design Review. Festive CDR season begins in May with our first critical design review, and I think we have 20 of those. So it's an amazing, amazingly complicated process. Now, here's the really key moment. Launch, August 2022, out of Kennedy in Florida, and you are all invited. I would like this to be the biggest launch party ever. How many of you have been to a launch at Kennedy? Anybody been to a launch at Kennedy? A few people. Yeah, so then you can attest, unless you're one of the VVVIPs, that what you do is you get bussed out onto a causeway and you stand next to a bunch of alligators 3 miles away from the launch pad and waiting for the moment. And I've only gotten to do this once, and I was a little worried that it was going to look like a tiny toy rocket going, you know, in the very big distance, but it is not like that. It's mind-blowing. Did anybody who go, did anybody who went to, anybody disagree with me? Is it not quite astonishing? Yeah, anybody underwhelmed, like, no. So for anybody who's excited by things like Formula One race car engines and that kind of just raw, unbelievable, inhuman power, this is like to the 1000th degree. It's unbelievable. And so we're going to launch either on an Atlas IV or a Falcon Heavy. We might launch on a big SpaceX Falcon Heavy with the recoverable boosters, which would be pretty fabulous, wouldn't it? Yeah, so they're getting safe enough that NASA would consider putting its... This mission, by the way, the PI managed cost, not including launch, is $760 million. And so they would not fly on a Falcon Heavy with recovered boosters, but they would let us fly with new boosters that we could then watch recover themselves, which I think would be pretty great. And so we're just now going through the process of choosing our launch vehicle. That starts next month. There's a guy who works at Kennedy. Here's a job aspiration for anybody looking for a job, whose job is rocket procurement. I think that's like the coolest job in the world. He came to one of our early meetings after selection. He goes, "Hi, Lindy, I'm your rocket procurer." And he gives me his card. So he's going to put out the request for proposal, and we'll certainly get those two. I think that's probably the only two requests that we'll get, and then we'll have to decide which one to fly on. I do not decide that. That is not in my duty. That is under NASA headquarters, and that's part of why the launch cost is separate. So that's what we're looking for, launch in 2022, and then we'll cruise out in the way that you saw in the film, and I'll tell you a tiny bit more about that, and we'll arrive at Psyche in January of 2026, and then we'll start orbiting. We'll orbit for 21 months, and we'll send back the data just the way Jim Bell said. So Jim Bell on that film, he's an amazing planetary scientist. He's been on practically every mission that you've heard of, and written a whole bunch of really great popular science books, by the way. And he's the deputy principal investigator for Psyche mission, and he's the lead on the imagers. And so the imagers are 2 cameras. We just, do you know how a lot of missions name each of their instruments something that's always an acronym? Have you experienced this? Well, I really, really hate that because I can never remember what they are. Plus acronyms, oh my God. So Psyche is not an acronym, obviously. It's the name of the asteroid. It's a goddess named after the goddess, originally in 1852 by its discoverer. And our instruments are named the imagers, the magnetometer, and the gamma ray and neutron spectrometer. They don't have special names. We actually know what they are. And so Jim's in charge of the imagers, and they're going to be built and tested at, first they'll be built at Malin Space Science Systems, but then they'll be at ASU for test. And so we're one of 7 universities that's actually can build and test NASA-certified deep space instruments on campus with students. And we do it behind big glass walls in that building we were talking about earlier, so you can see what's going on. So we'll be doing the imagers at ASU, and then ASU will be the data center. And so also glass windows looking at the data center. All the data will come to ASU before it goes out to the instrument teams and then back to the data repository. And we're pretty sure that we're going to be able to get the images out onto the web for public inspection within 30 minutes of our receiving them. So we are not going to hold them back and figure them out and clean them up. We're going to put them out for everybody to look at right away. So when Jim said that, he really meant it. Because we take it seriously that these are paid for with taxpayer dollars. And we want everyone in the United States, and in fact everyone in the world, to see and wonder with us at the same time. Because to me, the purpose of space exploration, and NASA tells me over and over again, and I have to say this, like my lawyer is looking at me saying, say this bit. NASA reminds me this is about fundamental science. This is how we learn how our universe is put together, by doing things like this. Going to the kinds of places where humans have never been before. We've been to Mars. We've got a pretty good idea of what's going on there. We can keep enhancing our knowledge, but it's really exciting to go to a kind of body that no one's ever visited. Fundamental science. But I think the real reason that we do space exploration is to inspire everyone on Earth to do more in our own lives, to be more bold. If we can do this, if we can have a team of 600 people who build something that flies through space without failure for year after year and then sends back information from this distant spot, then imagine what we can really do here at home. And so that's why I think we really do this, and I think we need it as humans to do this, to reach out. And so we're going to be sharing the images the second that we get them. All right. So here's the chassis for you engineering aficionados here. So this is the big box of the chassis is made of composites, and they bake them in these giant composite baking ovens up in Palo Alto at SSL. And you can see the dimensions here, 3.1 by 2.4 meters. So we're building an exact to scale replica of the spacecraft in our building at ASU, and it's going to be hung up in a giant atrium. And so we've got the aluminum framework of that chassis, and so when I stand on it, I can just touch the top. So it's a big box. It's a big box. And inside that chassis, you can just barely see them, are xenon tanks. So this is not a chemical propulsion mission. These are Hall effect thrusters. And so what is happening is we're using xenon, which is a noble gas, and we'll ionize them and then send them through a little potential field and out the back of these tiny thrusters, which you can see some right here. They've actually been moved. They're in a new position now in the new drawing. But they're not that big. They're like this big, and they make this beautiful blue flame, like straight from, it's a plasma, straight from sci-fi. And the tiny momentum transfer of that one little xenon atom coming out pushes the spacecraft forward just that much. So it's not fast acceleration, but it's extremely efficient. It's the most efficient kind of space travel. And we power that with the solar panels. And so if we were to unfold the solar panels, as we'll do after launch, that's the chassis right in the middle. That's still this. And these solar panels are the size of a singles tennis court if you lay them out. It's a big spacecraft. And at Earth, they're 20 kilowatts. And then out at Psyche, they're quite a bit less because of the distance from the sun. Now on this mission, of course, we've got our antenna. We've got to talk back to Earth. We've got our 2 magnetometers on this boom as far away from the spacecraft as we can get it, so we can also subtract out the spacecraft field and know if we're measuring the body. We've got the 2 imagers that peek out through this back panel, and then we've got a gamma ray and 3 neutron spectrometer tubes, and that amazing piece of equipment will tell us what the elemental composition of the surface is. And just in case you don't think that technology is unbelievable, that people have invented this, so this is how a gamma ray spectrometer works. Cosmic rays come through space and strike both the Earth and everything else in the solar system all the time. And some of them are very high energy. And they'll strike the surface of Psyche, and then they'll interact with atoms, and those atoms will then give off gamma rays and neutrons. And the energy of those gamma rays and neutrons will be detected by these detectors, and the energy tells you exactly what atom it is. And so iron will give a different energy of gamma ray than would nickel, so we'll be able to tell how much of each there is. But cosmic rays flood into the solar system from all directions all the time, and no one really knows how they're made. They come from outside our galaxy. Isn't that incredible? We can use these high energy rays that come from we don't know where and flood our solar system all the time, but we can actually harness them to figure out what this body is made of without touching it. I think that's pretty cool. So that's what we're doing. And then there's this really cool thing, the deep space optical communication. This is a tech demo that we're flying for NASA. It's a demo of doing communications with Earth using a laser instead of radio waves. Now, this is completely separate from our science. It can fail, and it does not affect anything in Psyche's mission, because we're using radio waves. But the idea is, from a distance of Mars, if you use laser, you can encode so much more information. It can be so much more data dense. People joke that that's how we'll send Netflix, streaming Netflix, to people who are living on Mars. So this is a very important test of this technology, and we'll be testing it all the way out to Mars during our trajectory. So that'll be fun to watch. So here's our process. So here's our launch in August of 2022. The orange part is called checkout, 90 days of checkout, where we make sure everything does what it's supposed to do. The blue dots is operating that deep space optical comm all the way out just past Mars. Gray is when we're using our ion thrusters. And then these spots are conjunction, when the sun is between the Earth and Psyche, and we won't be able to see it for a little bit. And then we just cruise, and then we thrust, and then we go into approach, and around January, we actually don't know the exact time because the thrusting and so forth with the Hall effect thrusters is a little bit inexact, but probably right around the first week of January, we will start to orbit Psyche. And we'll orbit Psyche while Psyche goes around the Earth all the way down to here in October of 2027, so for 21 months. So that's the trajectory and what we're going to be doing. And when we get there, we're going to start way up at, here's Psyche. That's approximately the shape of it. It's a triaxial ellipsoid. We have 3 good shape models for it. How, might you ask, could we possibly know the shape of something that we can only see as 2 pixels? I don't know, do you know? I didn't really know before. Some of you know. I know some of you know. We go to the beautiful radar dish in Arecibo in Puerto Rico, and we bounce radar off of Psyche, and we catch the return from Psyche. And then we measure how that return looks over time, and we can make a shape model. And by we, I mean other people, not me. But 3 different teams have done this, and they've come out with pretty much the same basic shape. So we do think we know what the shape is. So we're going to start very far away from it in orbit A, very high up. And during all of this time, the imager, the gravity, the magnetometer, gravity science, we're going to get the gravity field just by watching the radio communications with the spacecraft, actually doing Doppler with it, how the spacecraft is tugged by Psyche as it goes around Psyche. And so using those tiny changes in the radio communications, we'll be able to map the gravity field of Psyche. That's really, really important because you can't get a stable orbit if you don't know the gravity field. So we're going to start far away and determine the gravity field all the time, continuously. So we'll be taking pictures all the time as we go through the orbits. We'll be doing gravity all the way. We'll be doing magnetometer all the way, neutrons all the way, but gamma rays only at the very, very lowest orbit. So orbit A will stay up there for 56 days, about 700 kilometers above. Then we'll go down to orbit B, much closer once we've got the gravity and know that we can do that. We'll stay there. In orbit B, all of our requirements for the imager will be done, but we won't stop taking pictures. We'll just have concluded all the things we promised NASA we would do. And then in orbit C, we'll be down there even closer, just 170 kilometers above, and we'll complete all of our gravity and magnetometer requirements. And then finally, we'll go down to orbit D, where we'll be just one radius above Psyche. Really, really close, kind of a hairy orbit, because probably with something that's not really a sphere, and we don't know quite how non-spherical it is. We actually have done between, like, it's different tests, over 5,000 Monte Carlo simulations of how bad the gravity field could be, proving we can still get down to that lowest orbit and not be unstable. But it's going to be, as they say, sporty. We'll see how that goes. And so that's, oh, you know, this is something I knew it would be really hard for you to see, but I just thought it would be really interesting. This is timeline, 2021, 2022, 23, up to 2032. This is a timeline that we use to help us plan our launch and trajectory. Because here's an important thing for you to know about Psyche. Its spin axis, unlike being north-south and perpendicular to the orbit like the Earth's is, it's been knocked over. So its spin axis lies in the plane of its orbit, which means, like, if Anka is the sun, there's which you are, there's so Psyche, here's Psyche's spin axis. This means that right now only the north pole is Psyche spinning like a rotisserie. Only its north pole is in sunlight and its south pole is in dark. But then when you come around to the equinox, you know, then it's spinning like this, and Anka, the sun, can illuminate the whole side of it. And so this is a chart of the lighting conditions. And so greater than 90% of it is in light during these periods, during the equinoxes, and it goes down to less than 50% of it, maybe even 40 or 30% at its darkest periods when it's just facing its pole straight toward the sun. And so we really wanted to get there at a time when it was lit up. We didn't want to get there at a time when it was all dark. The gamma-ray neutron spectrometer will work no matter what, the magnetometer, but not the imagers. We want to see it in light. And so this is our 2022 launch, our beautiful 42-month trajectory for 21 months in orbit. If we waited until 2024 to launch, there isn't that good Mars assist, there just isn't that good trajectory, and it turns out it takes all these years to get there, and then a lot of the time we're there, it's even dark. And so finding a launch, and we also have a backup launch that's not that one, that will get us everything we need in science, that was tricky. So it's a really interesting problem, and I love that there are people who can do those calculations. That's kind of great too. And so I want to talk a tiny bit about outreach before I finish, because you might imagine from what I've been saying, something I think is completely critical for space missions is to include as many people as possible. Now, some years ago, Congress decided that space missions were not going to get actual outreach and education dollars. They're actually in their own part of NASA now. But what we do get is we get student collaboration dollars, and that allows us to do a lot of outreach. And so this is with permission, my good friend's daughter wearing a temporary tattoo of metallic Psyche on her hand. And so I usually have got a lot of those to hand out. And I wasn't even going to mention it, but now I have to. I forgot my temporary tattoos. But I would be so happy to send some up, and then they can be distributed to the devout here. So we have lots of swag, which is really fun. But then we have 4 major student collaboration efforts. And this is a new level of student collaboration that NASA missions haven't done before. We're trying to kind of push the boundary. One of them is Psyche Inspired, and these are creative arts students. We did it the first year just at ASU to pilot it and make sure we knew what to do. And then the second year, which is the year we're just finishing right now, we took it out nationwide. We can't go international with this, but we can go nationwide, and it's open to all undergraduate students at 2- and 4-year institutions in the United States. And we take applications, and then we pick 16. And those 16 artists get to make 4 original artworks based on the Psyche mission during the course of the year. And we tweet them out, and we put them on the website. We've got a great website filled with this stuff. And then at the end of the year, we have an art show, and we make a coffee table book. And we pay for all the materials and things like that. And it's been, I can't tell you, so much fun. We've had not just art students, but engineers and scientists and management and business people and just any kind of major there is. And we've had creative arts everywhere from giant sidewalk chalk artists to people who do paper art, original music. And this guy is a ceramicist, as you can see. And this is one of my favorite pieces. It's quite big. It's a big platter like this, and it's very, very heavy. And he really wanted to make a glaze that reminded him of what a metal object might have on its surface. And so he made a glaze out of thermite. Now, I know, so I could see from your faces that some of you know what thermite is. and unsurprisingly, it tripped the temperature sensor in the kiln and shut it off, but amazingly it did not cause a giant disaster. And what it did make was it made this amazing 3D patterned, superheated and then cooled glaze. And so things like this I just love, absolutely love it. And so here's the summary of the outreach that we're doing. So Capstone Projects, this, in the 2 years we've done this, we've had 260 undergraduate students on 42 teams in 7 universities. And so anybody here wants to run Capstone Projects with us, we would love to have you. What we do is we take real engineering problems from the mission and we invite people to help solve them. And we also really, really push for interdisciplinary capstone teams. So at ASU and at some other universities, I wonder if you have it here. Do you have an industrial management kind of major, like a project management major for undergraduates? I don't know, sometimes in the engineering school we have that. So we have that at ASU, people training to become professional project managers. So we get one of those students and we get a graphic designer and we get a marketer and a business person and we get an engineer and a scientist and we all put them on the capstone team together like real life. And then they have to solve problems. And so that's what we like to do with capstone projects. We've pretty soon we're going to roll out our very first smartphone application for Psyche project, and it was made by our first-year capstone teams. Those undergraduates actually made what is now a NASA certified product that's going to go up on the App Store, which I think that's pretty cool. So then there's Psyche Inspired. Those are the artists that I was telling you about a moment ago. Now, there's the Innovation Toolkit. This was my particularly subversive thing. So NASA and ASU Continuing Ed have teamed up to make free courses, online courses, available worldwide forever to anyone. And so the very first one we just rolled out last week, and it is the process and lifetime of a space mission. So if you'd like to learn more about that, you can go on our Psyche website and click through to the online course and take the course for free. And if you want to use it as like an intro to an aerospace course or something like that, you're welcome to use it any way you want. And so the next one is going to be the Inclusive Mindset, Tools for Building Positive Team Culture. Then we have outreach interns that do K through 12 outreach with us, which I think is really, really great. They mainly do it right on campus, though, not outside in other states. And we just want everybody to be as involved as possible. So you'll find all of these things on psyche.asu.edu, and including clicking through to the course. You can download sheet music that's been composed for us. We have all the videos, including the video you just saw, available there, and all of the graphics. A lot of the graphics are there too, the trajectory and things like that. And also we have a Twitter account and a Facebook account, and then I tweet also if you want sort of the up-to-date what's happening on the day-to-day. And this, of course, is one of the images by Peter Rubin of what we think these frozen spires on the edges of the impact might look like. And you can see this might be Palasite, and then in the background maybe that's a sulfur volcano. And remember what I told you, though, this is all almost certainly completely wrong, right? And then the other thing is 4.568. I know you all remembered that. Yeah, the age of the first solids in the solar system. Thank you very much for listening tonight.
Okay, so we have time for questions. So we're not going to use a microphone, so speak up.
And I will repeat. Go ahead.
Well, since it's such a tiny dot in these telescopes, how do you know it's metal?
That is such a great question. How do we know that it's metal? How in the world can we know that it's metal? Mostly we get composition from reflectance spectra. We watch the sunlight coming back and we can see the squiggles in the spectrum That doesn't really work for Psyche because Psyche has a very, very flat reflected spectrum. And so many things could have a flat, featureless reflected spectrum. So the reason that we actually think that it's metal and not just something like the other things with flat spectra out there is from radar, actually. The radar albedo, that is how much radar gets bounced back, is much, much higher than has been bounced back by any rock. And also its thermal inertia is extremely high. So it has a very different thermal characteristic than rocky asteroids. So those are the two things that make us think that it has to have connected metal. The spectra experts, the squiggle watchers, say that they think that it's 90% metal on the surface and 10% rock. But we really, really don't know. It could be just some weird material that we haven't run into before. But I really want it to be metal after all this thinking about metal. So cross your fingers that these radar numbers are right. We haven't been able to think of anything else to explain the radar numbers. That's why we think it's metal. How did we discover Psyche initially? When JPL sent me that email saying we'd like to propose a mission to test your hypothesis, the hypothesis in that paper was actually about the ways that planetesimals heat and differentiate. And so we started looking around the solar system for some place where we could find pieces of a planetesimal that had differentiated at some point. We wanted to find a family in the asteroid belt that had pieces of core and pieces of rocky mantle and maybe pieces of some sort of lid. It turns out that does not exist. And that is such an interesting problem. Why does that not exist? Why is there not something that broke apart and we can see all these pieces? So we gave up on that and we decided that the next best place to go would be what we think might be a core. And so that was Psyche, because there's only one Psyche. And so that's the only place to go to see this. Now, Psyche itself was discovered in 1852. I love to tell this story, so I'm going to just tell it. I hope you don't mind. By an astronomer in Naples named Annibale de Gasparis. I'm probably not pronouncing it correctly. I have to get someone Italian to teach me. So why was he looking for asteroids in 1852? Well, because, have any of you ever heard of Bode's law? There was this law that was in the late 18th century that was thought to predict the spacing of all the planets in our solar system. Now, those of us who have had any polynomial math understand that you can write a polynomial that will explain the spacing of any set of objects. But this guy thought he had really figured it out because the polynomial fit every planet except it said there should be one between Mars and Jupiter. And so this guy named Franz Xaver von Zach in Germany decided he was going to get all the astronomers in Europe together to find the missing planet. And they had a proper name, which I now forget, but their nickname was Die Himmelspolizei. They were the celestial police. They were there to set straight the heavens, to set it to rights and make it orderly again by finding this planet. And so they started searching, and then they found one Ceres, and they found two Pallas, and they named them in order. They numbered them in order. That's why asteroids have numbers. And they were all named after gods and goddesses. And finally, they got to 16 Psyche, discovered by this guy in Italy, and they went on for a little while, and then finally they're like, there's no planet. And then it was the end of Die Himmelspolizei. So that's the story of Psyche. That is such a great question. What was phase A is the question. Why did our timeline start with phase B? There is a technical NASA engineering process in phase A, which I forget what it is called. Does anybody remember what it's called? Something like dreaming or like writing on an envelope, some equivalent of that. But the way that they did the proposals, they counted our second proposal, that concept study report, they counted that as phase A. And then when they selected us, they let us go straight to phase B. So that's why there was no phase A on there. But it's in the course, the online course.
Why do you think there's like aluminum-26 that makes these cores differentiate, like if there's no more of it?
Why do we think that aluminum-26 made the cores differentiate if there's no more of it? Great question, and a question I was so excited when I finally learned the answer to it. So we've got these long-lived radioisotopes that we're used to, like aluminum and lead and potassium, that continue to decay in the present day, and we can measure them and kind of know what their decay rate is and stuff. But it turns out that at the very beginning of our solar system, there were a number of very short-lived radioisotopes that burned themselves out. And so how did we know that? Well, they were discovered predicted and then discovered by Urey in the 1950s, I believe. Do you remember I told you there were little like small pebbles that were the very first things to form at 4.568, right? And so those are called calcium aluminum inclusions, and they're made of the stuff that's going to condense first when it's hot and begins to cool down. The things that condense at the highest temperatures are those tiny first pebbles, and they contain a lot of aluminum, and they contain a lot of magnesium and calcium and some other things. And then those atoms form into crystals. And one of the kinds of crystals they form into in these tiny pebbles are a mineral called feldspar. And in those feldspars, they found some magnesium atoms. Now, for those of you who would love feldspars like I do, you will know that there's never a magnesium atom in a feldspar. It doesn't fit in the crystal lattice. And they looked and they found that those magnesiums were living in the crystal lattice right where aluminum was supposed to be. And they were magnesium-26. And then they did the nuclear physics and discovered that magnesium-26 could be the decay product of aluminum-26. So then they thought they must have originally formed from aluminum-26 that then decayed. And then people discovered that aluminum-26 is produced in supernovas. So when big stars go supernova, they make aluminum-26. So here's the scenario that we think happened. We think that a big supernova happened, and it made a shock wave filled with lots of elements, including aluminum-26, that banged into a giant molecular cloud, kind of like the pillars of creation, that beautiful, beautiful Hubble image, if you've seen it with those towers and all the star-forming regions. Like a shock wave bangs into one of those, and that gas begins to contract under its own self-gravity and form a solar system that then has the aluminum-26 in it right at the beginning. And so that's why we think, also iron-60 is formed that way. It turns out you can do the models, iron-60 is not energetic enough to melt anything. And there's no other explanation for the melting early in the solar system we can think of. Impacts do not give it enough energy. There's no other energy source. So we really think it has to be aluminum-26. It's such a mystery. That's a great question. Hope you don't mind my long answer. Yeah. Any other questions? Yes? Why would a liquid core not be dispersed into space during hit-and-run collisions? There are certain collisions that could break it into many pieces, but it turns out that those collisions, you're more likely to have them all self-gravitate back together again. And so it is also possible that it was kind of pulled out into some sort of crazy shape, and then it kind of slooshed back together again under gravity. So, what is Psyche? So is it a core that was stripped off and kind of reformed in that way? Could it be a little piece of a much bigger collision, but then where's the rest of the debris from that collision? And I'm told by NASA, so we were talking about this today, this is not really how science works often, that you have absolutely got a rock solid predictive hypothesis that you can test, and you do exactly that, and then you have an alternative that you can test. A lot of times, there's only one solar system. There's only one Earth. You can't do replicant experiments. So a lot of times you kind of go, oh, look, I think I'll just work on that because that I've got an answer for. Well, we don't have that luxury with this mission. We have this exact hypothesis we're testing. And we have to have, they made us have an alternative hypothesis. So if it's not a core, what could it be? Well, I guess my favorite option would be highly reduced material that formed very near the sun but never melted. But we really don't know. And so if any of you have good ideas about what else it could be, publish now before we get there. Yes?
Would the creation of the Earth's moon be an example of the destructive impact?
The creation of the Earth's moon, yes. And so the leading hypothesis for the Earth's moon is that some large object came and hit our young Earth and then basically made a spray of material that was orbiting all around our Earth and then recoalescing. And some of it recoalesced onto the Earth and some of it recoalesced into the moon. And so that is exactly the outcome of a different kind of impact. Yep. Yes?
Are you receiving any kind of comment from the international space community with this expedition?
Are we receiving comment from the international space community? Sure, absolutely. People are really excited, actually. And I'm amazed and thrilled by how excited people are about this mission, because there are a lot of missions going on. The European Space Agency had some proposals to also fly to Psyche, but we got selected first. And so we get to be the first in the world to go. We've got partners at the German Space Agency who are working with us on the team, which is pretty great. And then there'll be opportunities for people all around the world to work on the science, because we keep the science. What NASA does is we keep the data within the team for a few months to clean it up and make sure that it's really right, and then we put it into the planetary science repository where everyone in the world can go download it and learn from it. And so I love that. I think that it's a nation uniting activity. And the fact that everyone wants to go see something that no one's seen before, I think it's just in our human DNA to want to do that. So yeah, spreading it as far and wide as we can. Yes?
Don't you want to actually send something down to the surface?
Don't we want to send something to the surface? Nah. Who wants to bring anything back or stand on it or go there with a person or anything? No, we would love to. We would really love to. And there's a reason why we're not flying a CubeSat along, which would be fun to do, which it's boring. I'll talk about it later if you're interested. We would love to land on it. We would love to suction something off it and bring it back the way OSIRIS-REx is. But it turns out that at this price point, you can't do it. That's how hard it is to do things in space. So the reason that the Japanese Hayabusa mission, which is so unbelievably great, and University of Arizona, our neighbors, OSIRIS-REx mission, can go and return is because they're going to near-Earth asteroids. Those asteroids are way, way closer. They're Earth crossers. They come within Earth's orbit. This guy is way out past Mars near Jupiter, so we can't go out there and collect it and come back. But it's the first step to understanding what it is. One interesting thing to look for as we go is we do not know if metal surfaces make any kind of regolith. You know, that's what you call like a soil on another planet that has no organic material in it, call it a regolith. That's what they're going to vacuum up with OSIRIS-REx, because we know there are pebbles and things on rocky asteroids. But striking a metal object with the solar wind and micrometeorites over the age of the solar system may only anneal it. It might not make it crumble into little bits. So there may be no little bits on it. We don't know. So things to discover. Yes? What's going to happen when we're done with the spacecraft? Yeah, that's so when we're finished with it, what's the end of mission plan? And so we have a tentative end of mission plan, but that takes much, much agreement with NASA when the time comes. We thought about trying to take our extra xenon and fly onto another object. And you'd think, with the number of objects in the asteroid belt, that would be no problem. And I can't kind of get out of my mind the Star Wars flying through the asteroid field kind of thing. But of course, that's not what it's like. There's nothing near Psyche. Like, we can't actually go to another thing. Nothing that's relevant to us, and even the things that are possible to get there, it's really hard to get there. So we decided that the best thing for our science is just to go closer and closer and closer to the surface, getting better and better and better data. And so the Psyche-inspired art interns last year decided, in fact, they were invited by PBS to write a children's book about Psyche and then come down and read it on the air to a library group, which was so fun. So they wrote and illustrated a children's book, which you can download. And they had this giant crisis. You know, it's all about humanizing the spacecraft. You know, here's the spacecraft, you know, blasting off from there, so courageous, kind of frightened, going through space, not sure where it's going, finally meeting Psyche. And then, like, all the kids wanted it to go back home again, like, go home. But the artists decided that to be true, because I kept insisting that they could only tell the truth in the story, that they decided to tell it like Psyche the asteroid and Psyche the spacecraft just liked each other so much they decided to stay together forever. Yes?
When I walked in here tonight, I only had one question. Thank you. And I have 4.
Excellent.
Ask anyone you want. Just take your pick.
3.
3. Okay, disregards the aluminum, the short line aluminum. That means we're made, which do you prefer? We're made of stardust or space garbage?
Oh, that's a great question. So his question is, he had 4 questions. I picked number 3. He says that he asked, so aluminum-26, does that mean that we're made of stardust or are we made of space garbage? Oh, what a choice. Guess what? I choose stardust. That's what I choose. Yeah, you all know that, right? This is one of the most wonderful things to say, is that everything from iron on up in terms of weight of elements is only made in supernovas. And the universe only started with hydrogen and helium and a tiny bit of lithium. So none of the elements that we need for life or anything that we care about on a rocky planet existed until several generations of stars formed and then exploded and made the heavy elements so that we could exist. So the earliest stars couldn't even have planets because the elements didn't exist.
So who would like the final question? One more.
Number 2. Okay, no, what your favorite question, whichever one.
Okay, regarding the material that metallic asteroid is made of, it looks to me like the coloration on that has nothing to do with sulfur. I'm thinking that if in fact we find it for that one asteroid, suddenly our inventory of really nice industrial metals increases by a factor of 1 million or 1 billion.
Correct.
That might change the way we use those kind of industrial metals.
Correct. So the question is, the materials of Psyche, are they industrial metals, in fact? Well, so some of you may know that I've had a quote out there that the market and the metals market value of Psyche in January of 2017 was $10 quintillion. It was something like 6 or 10 times the entire global gross domestic product. But of course, that's a silly number, right? It means nothing. Because if you could bring that back, which we absolutely cannot, we have absolutely no way to do that. Absolutely no way to do that. It would crash the metals market, plus it would actually crash the Earth. It would be bad. Like, so nothing would be worth anything anymore. But if Psyche is made out of what iron meteorites are made out of, it's made out of iron and nickel, and copper, and cobalt, and gold, and silver, and rhenium, and iridium, and platinum, and a whole bunch of other really lovely things. And so it kind of adds credence to Elon Musk's idea, let's take our industry and put it in space and save our beautiful Earth for the things that only Earth can do. And maybe this is a first step.
You could pave the streets with it.
You could pave the streets with it.
Let's thank Lindy for that wonderful.
Thank you very much.